In this tutorial, I'm going to be outlining how to use MENOTR to determine parameter uncertainties. So these are parameter uncertainties. The idea here is that you've already performed a fit, and now you're wanting to generate some uncertainty on your fit parameters to determine how constrained the parameters are, perhaps. So here I have this example where we're just fitting a simple data set. We're fitting that data set to a line. The data set's well described by a line. And now the fit itself, here I'll show you here, has already been performed. And as you can see, the data are well described by a line. And I was able to extract out these two kinetic parameters, these two parameters, M and B, where we have M is approximately 19.86 and B is 2.45. And now we want to generate some uncertainty. So MENOTR has two different ways of determining uncertainty. The first is using Monte Carlo simulations, and the second is using a parameter grid search. And I'm going to outline how to do both of those here for these two parameters, M and B. So the first step here is you need to go ahead and carry out your fit however is necessary. So if you're using kinetic scheme or implicit fitting or however, you first carry out that fit how you've done previously in the other video tutorials. Now, this is the second step to this process, which is determining the parameter uncertainties. You now go into the parameter uncertainty scripts, and you actually go into this folder and copy over these two MATLAB scripts, which are step 4 for Monte Carlo and step 5 for grid search. And you copy these directly into your workspace. So now we have those here, Monte Carlo and grid search. So now if we go ahead and open up step 4, here we're going to be looking, the only thing you need to edit is this first section, which is an initialization. So we generally recommend that you try to do as many Monte Carlo simulations as you can. Here for this tutorial, I'm actually going to lower this down to just 300. And now in the second step here, or in section 1, the second component that you need to address is if you want to check for if two parameters are correlated. So here we can go ahead and check to see if these two different parameters 1 and 2, which correspond to M and B, are correlated or not. So to do that, we just put in those numbers 1 and 2. And now you simply press run. And as you can see in the command window, those Monte Carlo simulations have been generated and subsequently fit using your model. And now we're generating these plots. So now you can see histograms for each of your individual parameters, as you can see through here, where you have your parameter 1 and the different values that were generated from the Monte Carlo simulation, or fits to Monte Carlo simulations. So that's for parameter 1. This is for parameter 2, which correspond to M and K. Or excuse me, M and B. And now in terms of correlation, we can see, so if we go to, I don't exactly remember which one's which, so we can go through here. So M is the first and B is the second. So we can now look for correlation. And now if these parameters are indeed correlated, then we would expect to see, if we plot the parameter 1 versus parameter 2, then we would see this trend in the data where you would see that they would follow this line. As here, you're only seeing a modest shift of parameter 1 to parameter 2 being described by a line, which suggests that these are not highly correlated parameters. But they're certainly modestly. So that was parameter 1 versus parameter 2, or parameter 1 versus parameter 2 are shown here. And then parameter 2 versus 1 is shown here. Now, the actual fits themselves are shown here. So you can click on, or excuse me, the resultant Monte Carlo fits of the Monte Carlo simulations and generating the parameter certainties are shown here, where you have the mean and standard deviation, and those are shown here, where each row corresponds to a different parameter value. So this is the parameter 1 and 2. The first column corresponds to the mean, and the second column corresponds to the standard deviation. So we can copy these parameters over and put them in here. Oops. And as you can see, these are the fit parameters, and then this is the corresponding uncertainty. And how one would report this is we have 19.9 plus or minus. Oops. Let's see if I can get this. 19.9 plus or minus 0.1. And then we have 2.5 plus or minus 2.5 plus or minus 0.7. So now we've generated uncertainties for, here, I'll make this a little bit bigger so it's easier to see. So now, as you can see, we have now uncertainties on these two parameters M and B, and showing how constrained the parameters are. Now, if we want to do this in a different way, so using parameter grid search method, so if we shrink this, we can go ahead and clear our workspace. So clears the workspace shown to the right here. If we type CLC, it clears the command window. And now if we open that second script, which is the parameter grid search, you'll note that there's 3 stars next to section 1, which is the only section that actually needs to be edited in this script. So here, and there's only 3 inputs that you need to worry about. So the first is you need to define the parameter that you want to perform a grid search on. So let's leave that as 1. And there are these 2 additional parameters that you need to define. One is grid pointer or GRD PNT, and the other is div val. And grid point is how many points on your error contour you want to have. And this will be a little bit easier to explain once I perform this and show you the plot. And div val is the breadth of the points and their distribution along the error contour. So here I'll show you this a little bit more clearly in a second. So here we're generating that error contour. So now we're looking at the left side. And we're going to have 10 data points on the left side and then 10 data points on the right-hand side because we set this as 10. And now because this parameter is well constrained, I set the value at 2. So and what that means is, so if I have grid search plot over here, so as you can see, the number of data points to the left and right was 10, so that's what is describing here. So here, let's describe the actual axes first. So parameter 1 are the different values for parameter 1 that were considered, and these values were fixed. And then F calculated is a measure of how well is the ratio of the chi-square for having that parameter fixed for at a particular value, divided by the best chi-square when param 1 is allowed to float. So as a consequence, the ratio of the 2 is 1, and then you're looking at the increasing error on the fit line with the increasing values of param 1, either decreasing or increasing. So now what you're of interest is where the F calculated curve or the error contour generated here and where the F critical line intersect. And these data points shown here and here correspond to the 68% confidence interval points. And as you can see, we have a good spacing of the individual data points, so we can have confidence in these actual intersection points. Now, as I was saying before, GRD PNT or grid point is how many points to the left and right are on this contour, and then the div val corresponds to how broad this curve is. So if this value is raised, the error contour will become more wide across, or the values of the data points will become more spaced out. So instead of going from approximately 19.8 shown over here, then you have another one like 19.75. It might go from 19.8 up to 19.7, for instance. So you're spacing out the data points more with respect to the parameter value being investigated. So now once you generate this error contour, though, you can go over here into grid search confidence interval. And these 2 data points, or these 2 values, correspond to the lower and upper bounds for a 68% confidence interval. So now we can generate that here. So our fit parameter is 19.8, and then we have a lower bound of 19.6 and an upper bound of 20.06. And now we can do the same thing with the second parameter. So we can change this to 2. And now, so if we perform this here, okay. So now if we look at this grid plot, this confidence interval, you see that the F calculated data points never intersect the F critical. So it says that we're not surveying a broad enough values of parameter 2, so we need to space out the data more. So the way we can achieve that is by increasing this value. So you can increase it from 2 to, let's say, 70%. So this is normalized to the magnitude of the value you're looking at. So this is actually a percentage term. But so we can raise this to 70, and I think we might get something more reasonable. Okay, so as you can see, now we're serving a larger span of different values going from 1 to 4. And as you can see, now we're getting that classic curve of what we were expecting, and we can see clearly where that intersection is. And now we can extract out those values shown here, and we can put those into the spreadsheet. So now we have a 68% confidence interval where the lower bound is 1.8. We have a minima at 2.4, or the best fit parameter is there, and an upper bound of 3.1. So here I've shown you how to calculate both Monte Carlo, or how to fit, excuse me, I've shown you how to generate uncertainty using Monte Carlo simulations, as well as how to generate uncertainty values using a parameter grid search.